Let's start. So let me make some correction from the previous lecture. So we considered the same space having the two different versions of the basis vector. So the left ones and the right ones, right? And then these ones are orthogonal ones, and these ones are not. So they are just linearly dependent. And the left one is linearly independent. So the right one is a linearly independent, but the left one is a linearly independent, but also they are orthogonal. So when using linearly independent ones, not orthogonal ones, and then we have to solve this linear system, right? So it's a little bit messy, but you get the idea. But in the case of the orthogonal basis, and then the linear combination coefficients of C1 and C2 can be obtained separately from each other. So by using the first vector only and the given vector x, and then we can obtain C1. It's not dependent on the second basis vector that is orthogonal to the first one. Okay, and so this example is just involving two basis vectors, but even if we have more than two basis vectors, in the case the subspace dimension is more than two, and then we will have more than two basis vector, of course. And then in that case, if they are still orthogonal, and then we can also obtain each coefficient separately by only using the respective basis vector. And so I think we will see some more examples in the later class. Okay, so let's see. Okay, so now we discussed about the orthogonal projection, which is quite an important one. And so this is one of the main part in the whole chapter 6. So let me describe it as follows. So suppose we are given a non-zero vector u, and then we are given the vector y, okay? And then we consider some subspace spanned by this single vector u, okay? Okay, and then given this vector y, we can decompose this vector as a sum of these two vectors, okay? So given just any vector y, we can just decompose it into the sum of two vectors, and then the first vector is inside of the span of the u, okay? And then this z vector, it is not just belong to the span of u, but also it's actually it's actually the orthogonal complement of the previous subspace, okay? So it means, okay, so we studied some orthogonal complement, right? So consider we are given one subspace first, and then the other one within the same entire space of an Rn. Okay, so we consider the other subspace where, okay, so from W and W perpendicular, if we pick up any vector from W and then another vector from W perpendicular, and then these two vectors u and v are always orthogonal to each other. So that is the definition of the w perpendicular, or orthogonal complement of w. And then this theorem is not yet the theorem, but this slide is saying that. So within the same entire space, we pick up, or we are given any vector in Rn, and that is decomposed into the sum of the two vectors, where the first one is belonging to w, and then another one belonging to w perpendicular. Okay, and then in this slide we are looking at some particular example where w is spanned by only one vector, which means that w is a one-dimensional subspace. Okay, in other words, w is spanned by just a single vector u. Okay, and then let's just look at how we can obtain this y hat and z, where these two are satisfying these two conditions. And then because y hat is span is belonging to the span of u, and then of course this y hat is represented as the scalar multiple of this single basis vector. Okay, and then okay, in this figure, suppose we have this y, and then this is u. Okay, and then geometrically, this decomposition is just giving you, or considering, this point where this y is projected. I mean, y is projected orthogonally along this line spanned by u. Okay, so in this case, this angle is 90 degrees. Okay, and then we consider this kind of vector. Okay, so that vector is of course along the line spanned by u, and also this line, or this vector is represented as y hat. Okay, and then what is z? So z is y minus y hat. So we have y here, and then y hat here, and then y minus y hat, which is the remaining component will be this guy, right? So we are basically decomposing, or we represent one single vector as the first vector that is spanned by u, and then another vector, and these two vectors, the horizontal and the vertical one, will have 90 degrees. Okay. So that way, alpha u is in the subspace w, which is spanned by u, and then y minus y hat. So that is perpendicular, because we have a 90 degree here, that is perpendicular to alpha u. Okay. So that way it is belonging to w perpendicular. Okay, so in this case we can represent this equation, or this condition, as follows. So this guy is orthogonal to y hat, right? So from here, this is y hat, right? And this is a y minus alpha u, or y hat. So this guy is the same thing, and then this guy should be orthogonal to alpha times u, and then their inner product between this guy and this guy should be 0, and then we can move on. So y minus alpha u, and then this alpha u, the inner product between these two should be 0, and then this is a scalar multiple, and so we can move it to the left, and then we obtain this alpha y minus alpha u and u equals 0. And so yeah, we obtain this, and then if we manipulate this equation, then yeah, this guy should be 0 because they are perpendicular to each other. And so our alpha, okay, our alpha can be obtained as this guy. Okay? And then our y hat is obtained by this. And so it has this scalar multiple times the basis vector u. Okay, and then from y, if we obtain the y hat in this manner, and then this y hat is called orthogonal projection of y onto u. So we are basically projecting this y into this line spanned by u, and that point is called y hat, and that is called the orthogonal projection of y onto this u. And this remaining vector z, which is this vertical vector, okay, that vertical vector is another component. I mean the second component of y, because y was decomposed into y hat and z, and so z is another or second component of y, but that component is orthogonal to u. Okay, and then if we obtain alpha y hat in such a manner, and then this guy is not only perpendicular to y hat, but also it is perpendicular to any vector in W perpendicular, because any vector in W perpendicular, oops, so this is not belonging to W perpendicular. So what belongs to W perpendicular is the left side, right? So this is a W perpendicular, right? Okay, and then this guy, is always, perpendicular to alpha u, even when alpha is changing with the, to any other coefficient. So that's why, this guy is belonging to here, and this guy is belonging to here. So at least those two particular vectors chosen, determined in this manner, and those two vectors are, satisfying this, and so these two vectors can be, thought of being selected from W and W perpendicular respectively. Okay, so given any vector y, obtaining y hat, which is an orthogonal projection onto the line L spanned by a single vector u. Then if we view it as a kind of a function that maps y into y hat, and that function is written as projection or orthogonal projection onto the line L, and that is defined by this formula. Okay, so let's look at the example. So we are given y and u, and then we want to find projection of y onto the line spanned by u. Okay, so this is how we write this orthogonal projection, and then this guy is just a u dot u, and then u dot y, and the u, right? So basically, it should be represented as alpha times u, because that should be belong to the span of U. Okay, so let's just plug in each of these vectors into our formula, and then U dot Y is represented as this, and then we obtain this, and then obtain this. And so this guy is just 2 as the scaling factor. So the answer is 2U. So plugging this original U, and then we obtain this. And then this guy is a second component, right? So second component that we have. And then this vector, okay, this vector is perpendicular to 4, 2, right? If we, okay, so let me just redraw this, and then this Y is currently 7, 6. Okay, let me just draw it realistically. So 7, 6. We have the original vector Y here, and then U is 4, 2. So 4, 2. So yeah, so this is U, and so the orthogonal projection is as follows. So if we consider this a single line spanned by U, right? And then this point's orthogonal projection, like this is Y hat, and that Y hat is 2 times U, as we obtained here, right? So this is 4, 2, and this Y is 7, 6, right? And then this Y hat is obtained as 2, U, right? And then this guy is our second component that is orthogonal to the span of U. Okay, so this vector, this green vector, was obtained as -1 and 2. -1 and 2. And then just to verify, this guy, or this green component, is perpendicular to this subspace. Yeah, so we can just compute the inner product to just verify that their angle is 90 degrees. And then this guy, yeah, inner product with the 4, 2. And then, yeah, we can see that we have a 0 inner product. Okay, so yeah, so this is the same figure, and then this is the second component, and then we are actually considering this vector when the starting point is origin, or 0, 0. Okay, so that was a projection onto the subspace, spanned a single line. And then in the next chapter, we will see it's the extended version or generalized version where our subspace is spanned by multiple vectors, not by a single vector, where our subspace was just a single line. But if our subspace is a 2-dimensional or 3-dimensional, spanned by maybe 2 or 3 vectors, and then we can also perform this orthogonal projection of any point onto this subspace. And then the remaining component, or the second component, is always orthogonal to the original subspace. Okay, so we will see such an example. But before moving on, we have a few more to study in this chapter. The next one is this orthonormal set. Orthonormal set. So we studied the orthogonal set where any pair of the two vectors are orthogonal to each other, having 90 degrees. But in this orthonormal set, there is one more condition that is added, and that condition is that they are not just orthogonal to each other, but their lengths, I mean the length of each vector is 1. Okay. So that is the definition of this orthonormal set. Okay, so they are orthogonal, but their vector length is 1, which means that these vectors are unit vectors. So yeah, let me give an example. So previously we saw that this vector 4, 2 and maybe -1 and 2 are orthogonal vectors. So collectively, if we imagine like the set of these two vectors, they are orthogonal set, right? But they are not orthonormal set. But it is always possible to change any given orthogonal set into orthonormal set, because without changing the direction, we can just change the length of the vectors. And what is the length of this vector? So 1 squared and 2 squared, right? So it's 5 and the square root of 5, right? And so 1 over square root 5, -1 and 2. So this is the first vector, and then this guy, after normalizing it so that its length becomes 1, 4 squared and 2 squared. 4, 2. Okay, so these two are also normal set, where they are still orthogonal to each other, right? Because we didn't change the direction at all due to this scalar multiplication, right? And then their vector length has become just 1, right? So it's quite trivial and always possible to change any given orthogonal set into orthonormal set. Okay, and similar to, previously we considered the orthogonal set, and then considering the subspace, we thought about the orthogonal basis, right? Orthogonal basis. So similarly, if we define this orthonormal set, and then we can consider orthonormal basis of a given subspace. Okay, so if our subspace, one version of the basis vectors of our given subspace are this orthonormal set, and then these are called orthonormal bases. Okay, and then the simplest example of the orthonormal set is the standard basis for Rn. So if we consider R3, and then the simplest possible basis vector was this guy, 1, 0, 0, and 0, 1, 0, and 0, 0, 1. And in this case, they are actually orthonormal set, because if we compute the inner product of any pair of the two vectors, and then they will be 0, because non-zero entry is not overlapping between among these three vectors. And so the inner product between any two will be 0. And also, what about their length? Their length is always 1, right? And so this is actually orthonormal set. Okay. Yep, and then the last statement is saying that any non-empty subset of this orthonormal set or orthonormal basis is also orthonormal. Okay, so that is quite obvious. So if we have three perpendicular vectors to each other, and then if their vector length is 1, and then if we pick up just the two of them, which are just one subset of these orthonormal set, and then the subset is also orthonormal all the time. Okay, then these are some non-trivial example of the orthonormal basis of this R3. Okay, so this one is the simplest possible orthonormal set of R3, right? The entire space of an R3. And then this one is another orthonormal basis of the same subspace of an R3. Okay, if we verify them and then we just compute all the possible all the possible pairs of the inner products, and then we can verify that they are 0. And then if we check their lengths, this has a typo, so it is 1. Okay, so their vector length is 1, and any pair of these two, any pair from our orthonormal basis are having the 0 inner product, and thus we verify that they are orthonormal bases. Okay, then it can be viewed as follows. So if we think of this three-dimensional space, what is the standard basis vectors So standard basis was this guy, and this guy, and this guy. So 1, 0, 0, and 0, 1, 0, and 0, 0, 1, right? And then, what about these vectors, v1, v2, and v3? Yeah, they are actually these vectors, okay, these vectors, and they are different versions of the basis vectors that are also orthonormal set, right? Orthonormal basis, right? And so you can imagine this situation as, so we originally have this orthonormal basis, and then, yeah, so you can think of some kind of rotation transformation, right? For example, the first vector, this guy, was actually rotated as v1. Okay, so my v1, and then maybe this guy, v2, was also further rotated into v2, right? And then v3 is automatically, yeah, matching with the other one. Okay. So yeah, thinking of these kind of transformation between one basis vector into another basis vector. So that, yeah, you can think of it as a rotation. And that rotation vector, yeah, so let's just think of what kind of rotation transformation. I mean, let's define the specific rotation transformation in this particular case. So, I mean, it's a little bit of an additional topic, but yeah, you can view it. I mean, first of all, this rotation is a linear transformation. So we viewed, or we studied that this rotation in the 2-dimensional space is actually linear transformation, because like the linear combination of the inputs and rotating it, and that output is the same as first rotating the two vectors, and then after that we compute the inner product, and then those two vectors are the same ones. So this one can be viewed as like a high-dimensional rotation. So it involves rotating the first vector and rotating another vectors and so on. And then in that case, yeah, if we agree that this rotation transformation is linear transformation, and then any linear transformation can be represented as a matrix vector multiplication of y equals ax, right? And then how do you obtain A? So we learned about the standard matrix, right? And so simply our matrix A is defined as the transformation of the first unit vector, the second unit vector, the third unit vector, right? Okay, and then what is this guy? So we considered this 1, 0, 0 is actually rotated into this v1, right? And 0, 1, 0 is rotated as v2, right? And so simply just concatenating these three vectors column-wise, that is actually our rotation vector, right? So if we define this standard matrix that performs this rotation, and then that matrix can be used to rotate any given three-dimensional vector, right? So any given three-dimensional vector. So yeah, let me just give an example. So we already studied that in the case of two-dimensional space, if we rotate it into maybe 30 degrees, and then this 1, 0 will be rotated into maybe this guy, and this guy is rotated into this guy, right? And then we obtain the standard matrix as follows. This guy is negative. So this is our rotation matrix. right? Okay, so this was the rotation, right? And then this one is also rotating the standard basis vector into this v1, v2, and v3, right? So, yeah, so I mean, defining this rotation matrix in two-dimensional space is basically the same as defining the rotation matrix in the three-dimensional space, where we just rotate each of our unit vector 1, 0, 0, 0, 1, 0, and 0, 0, 1 into another vector. Okay, then let's look at the next theorem. So we are now given some rectangular matrix of m by n matrix, where this matrix has the orthonormal columns. So suppose we are given three vectors, three column vectors in our matrix, and they are orthonormal to each other, which means that their length is 1, and then their inner product between any given two will be 0. And in that case, U transpose U, I mean, if we compute this matrix multiplication, and then this matrix will always be identity matrix. Okay. And then let's look at the proof. And then if we view this U transpose, and then we have these three vectors as a row vector and the column vectors as a, of course, the original column vectors. And then let's view this matrix multiplication as the inner product perspective. So we have this first row and the first column vector that forms this guy, right? And this guy and this guy will form this guy. Okay, and then we can represent the resulting matrix element-wise in this manner. And then let's look at or check what particular value each of these components is. So this guy is 1 because it's inner product with itself. And then this guy is another one, and these are 1s. And what about these? Because they are orthogonal to each other, so they are 0 and 0, 0, and 0, 0, 0. Okay. Okay, so in this example, let's think of a little bit more in terms of the shape of this matrix. So in this case, the matrix U will be, it is just a rectangular matrix of having three columns. And these three columns are orthogonal to each other, and their length is 1, and they're unit vectors. And then this one is one example of m and n. So it's 5 by 3. Okay. So it is one case. And then what about the other case? For example, we have maybe 5 column vectors in three-dimensional space, and all these 5 vectors being orthogonal to each other, and they are unit vectors. So between these two cases, so let me ask the question: are these all possible, or any of them? I mean, is there any case that is not possible? Can anyone give an answer? So between these two, is there anything that is not possible? I mean that these column vectors should be orthogonal to each other, and their vector length is 1. Okay, so between these two, the second one is impossible. Impossible. And why? I gave you the answer first, and then let me ask why. So in this case, we have a 5 vectors that are orthogonal to each other in 3-dimensional space. In 3-dimensional space. So it is not possible. Because, so yeah, you can view this orthogonality as a kind of a more strict condition of, strict version of the linear independence, right? So as we saw earlier in this chapter, like the very first page, I think. Yeah. So orthogonal, being orthogonal guarantees that your vectors are linearly independent, right? So orthogonal by default just assumes that your vectors are linearly independent, right? So it's a much strict condition. So back to this case. Okay, so in this case, we have to if 5 vectors, so 5 vectors are orthogonal to each other, and then it means that they are at least linearly independent. So it means that we have 5 vectors that are linearly independent in 3-dimensional space, which are not possible, right? So just like, similar to the case where we can find, in the n-dimensional space, we can find, up to n linearly independent vectors. Yeah, similarly, we can find up to n orthogonal vectors in n-dimensional space, right? So this one is not possible. So this matrix that has orthonormal columns or orthogonal columns, okay? In that case, the matrix is either square in maybe 5 by 5 matrix or 3 by 3 matrix and so on, and also it is rectangular, such that this vector is very long and thin matrix. Okay, so this number should be always bigger than or equal to this number. Okay. Okay, and then what is this identity matrix? The size of an identity matrix. So in this case, because we are just transposing the matrix and then multiplying it on the left, and so the matrix size is always this 3 by 3 matrix, which has the size of the smaller size between m and n, right? So it's always n by n, which is a smaller number between m and n, right? And that number is 1, 1, 1, 0, 0, 0, 0, 0, 0, right? Okay, and then so in this case, difference between being orthogonal and orthonormal is really trivial. In this theorem, what if our matrix U is, U has orthogonal columns, not orthonormal columns. Okay, so the situation is that our vectors are orthogonal to each other, but their vector length is not necessarily 1. So in this case, what about this U transpose and U? And then, this resulting matrix will still be diagonal matrix, right? Because all these parts are, still 0. And those diagonal matrix is representing the squared length of each vector, right? But still, that is diagonal matrix. Okay, and then let's move on to this next theorem. So theorem 7 is having these 3 components, and so we now consider the linear transformation defined by U. Okay, so I'm thinking of this UX, where U has orthonormal columns. Okay, and then let's look at this example of our U. And then first of all, let's think of the dimension of these input and output vectors. So in this case, of course, the input vector is what? 3-dimensional vector, right? 3-dimensional vector into this 5-dimensional vector, right? Okay, and then this guy is like, our x is maybe 1, 2, 3. Yeah, so let's look at this example. And then the vector length of this 3-dimensional vector. And then we will apply this 5×3 matrix as U. And then this guy is something, some vector, some 5-dimensional vector. So this is saying that the vector length, or this norm, is not changing. The norm doesn't change even after this transformation. So this guy is again 3-dimensional vector, and this guy is a 5-dimensional vector, but the vector length doesn't change at all. Okay? And let's look at the proof briefly. So proof is simple. So this guy, we first take the square of it. Okay, and then this guy is represented as this UX transpose and UX, because once we take the square of the norm, and then we can change it into the inner product with itself. And then this guy. Okay, and then this guy is X transpose, U transpose, and U and X, right? And then what about this matrix product in the middle? So we already obtained that, or we studied that this U transpose U is identity matrix. Okay, so this guy becomes identity matrix, and thus X transpose X is the same as the original one. Okay, but its physical meaning is that the vector length, even after the linear transformation through this matrix U that has also normal columns, the vector length didn't change at all between this 3-dimensional vector and the 5-dimensional vector. And then let's look at this another one, and it means let's look at the physical meaning first. So we are given these two vectors in the 3-dimensional space. Okay, so in 3-dimensional space, we pick up any given two vectors, and then we compute the inner product between them. And then that inner product is actually doesn't change at all, even after we change this vector x through our transformation U and y. Transforming y through matrix U, and then the inner product will not change. Okay. Let's look at the proof briefly. So proof is almost the same. So we just, so this guy is X transpose and U transpose, and then U and Y. And then this guy is becoming identity matrix, and thus is X transpose Y and X and Y. Okay? Okay, so combining this item A and B, we can obtain another interesting characteristic of this transformation defined by this matrix with the orthonormal columns. So in the first item, that said that, that is saying that the vector length doesn't change at all. Okay, so if we are given the two vector x and y, and then their transformation into 5-dimensional vector, the vector length will not change at all, right? And then the item B is saying that those two vectors inner product remains the same, right? And so in the previous, input space of 3-dimensional space, the inner product between these two vectors, okay, is the same as the inner product between the 5-dimensional vectors, right? And then in the first item, it said that the vector length doesn't change at all, right? And then what is also not changing? I mean, yeah, what remains the same as well. So the inner product is represented as the product of vector lengths times 1. This guy is represented as this. Right? And then we consider this a ux and uy. And ux and uy and maybe cosine, maybe theta prime, which is a different angle. Okay, so this is of course a angle in the 3-dimensional space, and this guy is angle in the 5-dimensional space. But we know that the length doesn't change at all, and then the second one is saying that the inner product should be the same. So altogether, those two should be the same, and then yeah, those two parts are the same, and thus this guy and this guy should also be the same, and that means the angle between the two vectors doesn't change. Okay, so the vector length is preserved, and when considering the two vectors and their angle, this angle is not changing as well. So that is a little bit interesting property of this matrix transformation that has the also normal columns. And then this third one is a little bit of a special case where this x dot y is 0, which means that these two vectors have the 90 degree as the angle, and thus this 90 degree will also be preserved even after this transformation, and thus their inner product should remain the same because their angle is still be 90 degree. Any questions so far? Okay, and then so this transformation is actually this transformation is understood as the isomorphism. So what was isomorphism? Do you guys remember? Isomorphism. So we need to find the subchapter about the coordinate system changes. So which chapter was it? Change of basis or coordinate changes? (2-5요) 2-9? sorting. 네. Oh, wow. Yeah, okay. So I just wanted to think of this figure. So you guys understand this? So what was that? So when thinking of the linear transformation, okay, linear transformation. Okay. Okay. So, yeah. So suppose it's a 3, 1. I mean, this is an input space, and then we are transforming it into three-dimensional space. And then in this case, 3, 1 is represented as the linear combination of the simplest possible basis vectors of 1, 0 and 0, 1, right? And then these are the linear combination coefficients, 3 and 1, right? And then in this case, geometrically, this guy is like 3, 1 is over here. Then the first basis vector is this guy, and then this guy times 3, and this guy times 1, right? So that way we can obtain, or we can draw this parallelogram, where this parallelogram is especially like rectangle in this case, because we have these two like also normal basis vectors. So now we know that these two vectors are also normal basis vectors, right? And then let's think of the matrix transformation defined by our U. And U is composed of also normal columns, right? And that means, as we saw in this case, yeah, if we view this this matrix U having also normal columns, and then it can be viewed as like maybe 1, 0. I mean, if we consider this also normal matrix as 3 by 2. So in this case, what is the first matrix? I mean, first vector. It can be viewed as the mapping from 1, 0, and then this one is a 0, 1, right? And so back to this example. So this, so I have to use this this wall because I cannot I cannot draw more lines in this slide because it will be even messier. But anyways, this vector is actually transformed into this V1, right? V1 in the three-dimensional space. Okay, but now this three-dimensional vector is having a vector length of 1, and this guy is orthogonal to the second vector as well. Okay, what about the second vector? Second vector is mapping from mapping of this another unit vector, another basis vector into this vector V2, right? And now, if our matrix U has orthonormal columns, and then these two vectors will also have a 90-degree angle, and then their vector length is what? 1, right? And then you understand this like so if we have a 3, 1, and then we can draw this rectangle, and then now this guy, I mean this 1, 0 was actually changed with this vector, and this one is V1, and this one is maybe V2. Let's suppose that is in the three-dimensional space, and then what about these 3 and 1, and then this point 3, 1 will be mapped into like this vector times 3, and this vector times 1, and this point, right? You guys know that, right? This geometric kind of characteristic. And then let's think of this. We compute, this guy is one vector, and then let's think of another vector, maybe 1, 1, 2, and then where is this guy is moving to? This guy is moving to like this guy, right? Okay, and then now in this transformation, we think of the vector length and the angle between the two. So in this case, the vector length was this guy, right? So it's like maybe 1 squared and 3 squared, the square root of 10, right? And then what about this vector length? This vector length has increased, right? The vector length became larger, right? So in general, the vector length changes after this linear transformation, right? And then what about the angle? So between these two angles, this angle looks like maybe 45 degree or something like that, right? And then what about the angle between these two? These two are less than 45 degree in this particular case, right? Okay, so now let's think of the matrix transformation having also normal basis. So in that case, those two unit vectors, I mean these two also normal bases, are also mapped into also normal bases in, I mean also normal vectors in somewhere in the 3-dimensional space, or it could be like a 4-dimensional space in case our matrix is a 4 by 2, and then the two like 4-dimensional vector will be orthogonal to each other, and then their vector length is 1, right? So in that case, those two vectors that are transformation from the unit vector of 1, 0 will be mapped into this guy, and then 0, 1 will be mapped into the second one. But still, those two basis vector will have the vector length of 1 and having the 90 degree of an angle, right? And then what about these parallelogram? Okay, so in that case, yeah, so it is 3, 1, right? And so, and this guy, right? So this guy is the transformation of this guy, and then this 1, 2 is transformed with this guy, right? And so you can view it as like a moving or changing this coordinate system originally in the 2-dimensional space, and then just bring it, okay? Just to bring it, and then embed it into higher dimensional space, which is like this kind of a isomorphism thing, right? So what was isomorphism? And we can think of always like a 1-to-1 mapping from one point here and then another point over there, right? So yeah, similarly, this is a kind of a one example of the isomorphism. But in this isomorphism thing, the vector length was not changing at all, and also vector angle. From here, it is a 45 degree, and also here, the angle here is also 45 degree. Okay, so that is kind of hopefully interesting geometric kind of interpretation or the understanding of the matrix transformation with the orthonormal columns. Any questions? Okay, so that's it for the second chapter. And then let's move on to the third chapter, orthogonal projection, that we already studied in the previous chapter. But in this case, the main kind of main subject is about orthogonal projection to the subspace defined by more than one basis vectors. So orthogonal projection onto the subspace whose dimension is more than 1, right? So we are dealing with a little bit more general kind of case. Okay, so if the previous case of an orthogonal projection was like projecting from one point to like the subspace spanned by a single vector u, and then we can think of this orthogonal projection, and that was y hat, right? But now our subspace is spanned by these two-dimensional kind of subspace. So basically our subspace is having like two-dimensional, and then what about the orthogonal projection of y onto the subspace W? So we can think of this orthogonal projection having a 90 degree over here, right? And then similarly, we can decompose this original vector y into two pieces. I mean the sum of the two vectors, where the first one, okay, this first one is belonging to w, and y minus y hat, which is this thing. Okay, this thing. So that thing is this guy. Okay, that is belonging to w perpendicular, right? So that means this guy and this guy should be orthogonal to each other, right? Okay, so in this chapter, we will study how to represent this y hat. So previously, how is this y hat represented? Y hat was so project of y onto a line spanned by u, right? So I mean, I'm just rewriting the equation that we derived. So it is like u dot u and u dot y and u, right? And then there was the case where our subspace was spanned by a single vector, but what if our subspace spanned by two or more vectors? Okay. So this is the situation that we want to consider in this chapter, and I'm not sure if I mentioned about it, but this y hat is called in Korean. 이거 얘기했나요? y hat 이 수선의 발. 네. 이거 얘기했죠 지난 시간. 했나요? 안 했어요? 누구는 끄떡이지 않으면 아니라 그러면 뭘 믿어야 되죠? 네, 어쨌건 수선의 발. orthogonal projection은 이제 수선의 발이라는 뜻이에요. 그리고 수선의 발은 라인으로도 우리가 수선의 발을 내릴 수도 있고, 평면, 2차원 평면으로도 내릴 수가 있고, 네, 심지어 수선의 발은 3차원으로도 내릴 수가 있어요. 3차원으로 수선의 발을 어떻게 내리나? 그러니까 뭐 여기 있는 포인트가 이제 3차원으로 수선의 발을 어떻게 내리나? 3차원은 어디 있는 건가? 얘가 살고 있는 스페이스가 3차원인데 뭐 그래서 하여튼 어떤 부분 공간으로서의 이제 3차원은 이제 우리가 살고 있는 이 3차원에서는 3차원 부분 공간은 전체 공간이기 때문에 이 전체 공간으로의 프로젝션을 우리가 좀 쉽게 생각할 수는 없는데, 그렇지만 우리가 뭐 4차원 혹은 뭐 예를 들면 100차원에 살고 있고 3차원의 이제 부분 공간으로 이 orthogonal 프로젝션을 혹은 수선의 발을 내릴 수가 있어요. 네. 뭐 3차원에서 2차원으로도 내릴 수 있듯이 뭐 한 4차원에서 3차원으로, 뭐 100차원에서 5차원으로 다 내릴 수가 있어요. Okay, so we will study this orthogonal projection onto the subspace whose dimension is more than 2 or even more than 3 and so on. Okay, so in order to consider or in order to obtain this y hat, we first assume that we are given orthogonal basis of our subspace W. So the initial situation is that our subspace W has this orthogonal basis. Okay, and then this y hat is actually obtained in this form. Y hat is obtained in this form. So so this y hat is basically even though it looks quite complicated, it is basically a linear transformation of our basis vector of subspace, because we have those basis vectors of u1 through up, and then even though these terms look quite complicated, but once we compute them, they are just scalars, right? They're just the scalar values. Okay, so this representation is just a linear combination of our basis vectors, right? And so we can understand easily that this form of y hat is belonging to w hat. Just w. Y hat is belonging to w, right? Because it's a linear combination of the basis vector of W. And then what other conditions should we satisfy? Okay, that condition is as follows. So if this guy was our orthogonal projection, okay, and then that point should not only belong to W, but also this second component, y minus y hat, should be orthogonal to our subspace, right? Which means that this angle is 90 degrees. And that angle is, that 90 degree angle is not found just there, but also that angle is found in this case, or maybe in this angle, and so on. So that means, so what is the meaning of orthogonal projection onto a space, onto a plane, right? So we are given a single point, and then we are given a plane, and then we projected it orthogonally onto our subspace, and then that single line should have the 90 degree angle with any lines in our subspace. So the meaning of a line being perpendicular to a plane is that we pick up any line from our plane, and then that angle should always be 90 degrees. Okay? So that means this vertical vector, that vertical vector should be perpendicular to any given vector chosen from W. Okay? So you pick up any vector from W, which is our subspace, and that vector should be orthogonal to this vector, this green vertical vector. Okay. Okay, so that's a kind of high level kind of understanding of the characteristics of this orthogonal projection. But let's get back to this example. Back to this theorem. So we have the definition for y hat. Although we didn't prove them, but yeah, let's just take it as granted without any proof. But we will actually prove the other way. So yeah, let me show how. So this is a y hat, and then we want to prove that if y hat is defined in this manner, and then y minus y hat is orthogonal to any vector from W. Okay, any vector from W. So any vector from W, if this vector should be orthogonal to any vector from W, and then what equivalent conditions, and then this vector should be orthogonal to each of our basis vector of W, right? So in other words, if we choose any vector from W, and if that vector is always orthogonal to the given vector of y minus y hat, and then there can be infinitely many cases, because we can choose infinitely many different vectors from W, but in order to satisfy that, we can just satisfy only a finite number of requirement, which is that we have a finite number of basis vector of u1 through up, and then those are perpendicular to or orthogonal to y minus y hat, and then that is equivalent to the situation that we have these y minus y hat is orthogonal to any vector from W. Okay, and then let's just okay, so let's just look at that kind of condition. So y minus y hat, where y hat is an orthogonal projection of y onto the subspace W. Okay, so that is this C is this vertical vector. Okay, that vertical vector, and that vertical vector should be orthogonal to the first basis vector u1 and u2 and u3 and so on. And then let's just form form this equation, and then their inner product where the z is defined as this guy, which is a vertical vector, and that is orthogonal to u1, and their inner product should be 0. And then we write it. Okay, and then this guy is y dot u1, and then what about this guy? Y hat dot u1. How do we compute this guy? Okay, and then this y hat is at least a linear combination of our basis vector, because at least this y hat should be inside of our subspace, right? And then we are not just obtaining this y hat as some vector inside of the w, but that y hat should be our orthogonal projection that makes our z vector, which is a vertical vector, being orthogonal to any given vector in w. So that's why we are computing this guy and setting it as 0, right? But in general, any any vector from W can be represented as this linear combination, right? Okay, and then this guy, and what about the y hat and u1? So let's just think of the inner product with the u1 with this linear combination. Okay, this linear combination. And then this guy will have some value or non-zero value, but this inner product between u1 and u2 will be just 0, right? They will just become 0. Okay, and then after doing this inner product, the only remaining term will be c1 and u1 dot u1. Right? That's it. Okay? And so this guy, y minus u1 and minus this c and u1 dot u1 should be equal to 0. Right? And then what about c? How do we obtain c? Okay, so from this equation of like this guy, okay, from this guy, we obtain c as what? u1 dot u1 and y dot u1, right? So that's how we obtain c1, which is the linear combination coefficient of this guy. Okay, similarly, c2 through cp's are all obtained following this kind of form, right? So that's why we obtain the linear combination coefficient as this guy, these guys. Okay, so which conditions or requirement, which conditions led us to this kind of a representation? I mean, the main kind of equation that we used was this kind of constraint, so that this c, or this vertical vector, right, y minus y hat, which is the remaining kind of component, so that should be perpendicular to any given vector in W, which means that that vertical component should be perpendicular or orthogonal to each of our basis vector in the subspace W, right? So we obtain this, and then z inner product z dot u2 becomes 0, and so on. So that will give us this linear combination representation as this, and thus this representation is our orthogonal projection onto the subspace spanned by more than one vectors. Okay. Okay. So any questions about it? So, in addition to what we just studied, what we just understood, this theorem is saying slightly additional things. That additional thing is as follows. So we consider the issue of an existence and also the uniqueness about this orthogonal projection. Okay, so the question is whether the orthogonal projection does exist, or sometimes is it possible that this orthogonal projection doesn't exist at all. Okay, so that is about the existence problem, and the uniqueness is about, okay, so do we have multiple different orthogonal projection points, or do we always have a unique representation? So this theorem is saying that in terms of an existence, orthogonal projection is always existing, and also orthogonal projection is always defined as a unique one, because that unique one is having this kind of closed form solution, which means that once you compute, once you just plug y and u1 through up's, which are basis vectors, and then obtain that exact formula, and then that vector will be uniquely defined as a single vector, and thus it is unique. And also, this one is always obtained. It is always possible to just write that formula and plug our vectors into that formula, and thus it means that that vector or that orthogonal projection is always existing, right? So it always exists and unique for the orthogonal projection of any given point onto the subspace defined by a particular basis vector. Okay, so that's it for today. And so, we have a new homework, right? And then, Okay, so, see you next Tuesday. Okay, thank you.